So, next we are going to discuss about 60 gigahertz channel in details in presence of noise. So, from the previous slide what we have seen that because of this higher frequency we have very high attenuation due to path loss, and it is 28 dB higher compared to 2.4 gigahertz. And if I compare this value because of the attenuation due to atmosphere, that is only 10 to 12 dB per kilometer. So, much higher compared to that value. So, channel performance at 60 gigahertz, the first problem we will be facing is high path loss value. Then multi-path fading effect, we have human shadowing effect. Human shadowing effect, it can be as high as 20 dB. So, if let us say there is a link and any human is now present between the transmit and receive antennas, then the received power it can degrade by even as high as 20 dB. So, that we have to keep in mind. Then non line of sight propagation, that is due to multipath, non negligible Doppler shift even at pedestrian velocities, because we know delta f change in velocity, Doppler shift change in frequency, that is delta v by c into f naught. And also we have effect of noise. So, this noise it becomes an important issue. We will discuss in details about this noise. There are many sources of noise: thermal noise, it can be short noise, flicker noise, black body radiation. So, what is black body radiation? Because of the temperature of different object, they are constantly radiating. We can model them by black body radiation curve, Planck's law. And antennas, receiving antenna, it will collect this radiation as well, and it is a undesired signal and noise for the system. Then theoretical maximum rate at which error free digits can be transmitted over a bandwidth limited channel in the presence of noise, it can be given by Shannon's law. It is channel capacity C, it is equal to bandwidth of the channel multiplied by log, you note down here base is 2, log of 1 plus received power P r x divided by bandwidth multiplied by n naught. N naught, this is noise per hertz. So, total received noise is bandwidth multiplied by the n naught value, small n naught. So, approximately it is equal to 1.44 divided by received power by total received noise power. Here we are considering only the effect of thermal noise. So, n naught it represents thermal noise. We can also call then this P r x by capital N naught, this term SNR of the receiver, signal to noise ratio at the receiver. So, this formulation when we assume that bandwidth is sufficiently high tends to infinity. So, SNR it becomes one very important quantity. Channel capacity it depends on this value, and already we learned how to calculate SNR in presence of noise. So, the ratio of the signal power to the noise power at the receiver in dB is SNR, this is Pt, G of transmitter, G of receiver minus, now the path loss we are dividing it into two components, PL naught and PLR. Why? PL naught it is represent the path loss at 1 meter, and then after that we have a different coefficient n for path loss calculation. We call it relative path loss at r meter. So, for the first 1 meter we will consider n equal to 2 in that path loss formulation, that means 20 log 10 4 by r by lambda, and for the next part after 1 meter we have to experimentally determine what is the value of n. It usually varies between 3 and 5, which we discussed earlier. So, now why for first 1 meter we are using Phillips equation directly. If we have any transmitter, it can be placed on top of any pole outside or inside even any room. Let us say it is placed at one corner of the room. So, at least for first 1 meter we can consider it is unobstructed, and we can use the Phillips equation. So, after that we will be considering the effect of all this multipath effect, fading effect, human shadowing effect, and we will consider a different value of n. So, that is why we are dividing this path loss component into two parts. First part due to the first 1 meter from the antenna, and second part after 1 meter. Next is the IL. This is we call implementation loss. So, it represents all the losses in cables, antennas, etc. Then we can calculate the noise contribution. We are calculating SNR. So, we are subtracting now the noise component. Now, there are different sources of noise for any given device. If we have antenna, it has metallic part, dielectric part, it will add some noise. If we have cable, again inside cable it will add some noise. If we have amplifier, it will also add some noise. So, the noise contribution and how to calculate the overall noise we will discuss after this in detail. So, sometimes some devices it comes with its noise factor. So, noise factor is nothing but it is a ratio of SNR at the input terminal to SNR at the output terminal of the device. If the noise factor is given, we can directly put the value here. So, now the thermal noise, it depends on the effective noise temperature of the system and the bandwidth. If we increase the bandwidth of the system, we will pick up more thermal noise. So, we have to then subtract these two components, one due to thermal noise and another one which is coming from the active devices, which is given by noise figure of the device. So, then in this expression we have minus 10 log 10 kTB, we are using decibel scale, minus noise figure, we are assuming noise figure is given in decibel. Once we have this information, we can calculate then SNR, signal to noise power at the receiver, and we can calculate then what is the channel capacity for that particular given channel. Let us take one numerical example. Let us say transmit power is given as 10 dBm. So, 10 dBm in milliwatt, it is 10 milliwatt. Noise figure, this is overall noise figure is already calculated and given 6 dB. Implementation loss IL is given 6 dB. Thermal noise we can calculate K into T, it comes 174 dBm per hertz. Bandwidth of the system 1.5 gigahertz, and distance between the transmit and the receive antennas 20 meter, and the path loss at 1 meter, which is PL naught. If I put the values at 60 gigahertz and consider n equal to 2 in that expression of path loss, it comes 57.5 dB. Now, here is the plot of channel capacity in bit per second versus distance. So, for these specifications we will consider r equal to variable, and we are changing it from let us say 1 meter to 20 meter, and we are considering different scenario for indoor model. Inside office, for line of sight communication, n, that path loss index in Friis equation it was n equal to 2. Here inside office we are considering n equal to 1.77, and for non line of sight communication it can be via reflection, n equal to 3.85, we have higher loss. So, these are some experimental values. We are considering then indoor communication inside, let us say, office building. Now, let us see how the channel capacity it varies with distance for this given specification. So, this black line, solid line, it represents the free space path loss according to Friis equation, and we see if I increase distance, then noise power it does not change, but receive power it changes, it decreases. So, accordingly channel capacity it decreases. So, at 20 meter it is somewhere in between 10 to the power 8 to 10 to the power 9 bit per second, even though bandwidth is given 1.5 gigahertz. And you see for line of sight communication, indoor communication, n equal to 1.77, more or less it following the curve for n equal to 2, but for non line of sight communication, when n equal to 3.85, if I follow this blue line, it decreases to 10 to the power 6 to 7, somewhat in between this value at 20 meter. So, you see the effect of noise and distance. If we have higher n, then SNR decreases, as a result channel capacity also decreases. Now, we are considering another scenario. Here we are plotting channel capacity, theoretical channel capacity versus antenna gain. So, what is the minimum antenna gain required to maintain a given channel capacity of 5 Gbps? So, 5 Gbps is my target. So, for that we need to maintain a typical SNR value, and we are considering, let us say, the separation between the transmit and receive antenna is 20 meter. So, then SNR, if I consider the specifications given above, only thing is that we will change the receive and transmit antenna gain, and we are assuming receive and transmit antenna they have the similar gain, same gain value. So, if we need to maintain now this 5 Gbps data rate at 20 meter, we have to maintain the gain receiver transmitter gain value, typical gain value given by these curves. For example, let us say n equal to 1.77, this black dotted line. So, for 5 Gbps channel capacity, antenna gain required at least it somewhat, this is 15, 30, so 23 dBi both for transmit and receive antenna. Now, if n equal to 3.85 for non line of sight communication, minimum antenna gain it increases to 37.5 dBi if we need to maintain that 5 Gbps data rate at 20 meter. So, here what we are considering, that we do not have any control over transmit power and other things, only thing we can change the gain of the antennas, and this plot shows then what should be the minimum gain of the antennas to maintain this 5 Gbps data rate at 20 meter separation. A typical 60 gigahertz measurement setup, it can be anything. for this example we are considering, let us say we are going to characterize one antenna which is separated from the transmitting antenna at different distances. We are considering transmitted power is 0 dBm, that means 1 milliwatt. Attenuation loss of the coaxial cable 6.2 dB per meter at 60 gigahertz. Conversion loss of the mixer. So, you see in a typical system at millimeter wave frequencies, we know that at millimeter wave frequencies the component cost is very high. So, for any given system, then what we do, we try as soon as possible to down convert the frequency. So, just after antenna, it may be a band pass filter or a low noise amplifier, then we use a mixer to down convert the frequency. If you look at any practical instrument, for example, let us say a spectrum analyzer, inside the first stage it might use one mixer to down convert the frequency. So, once it is down converted to lower frequency, then we can use cheaper low frequency components. So, in this example also we are using a subharmonic mixer for down conversion, and mixer it comes with some conversion loss. So, if you feed some power to mixer which is millimeter wave power, when it will down convert to microwave frequency or RF frequency, then the power available for that RF or microwave signal, it will be much less compared to that millimeter wave frequency. So, for this one the loss, or because of this change in frequency, the which we call the conversion loss of the mixer, it is 40 dB. So, RF power available, it is 40 dB down compared to that millimeter wave power at the left hand side. So, this is a typical value for a passive subharmonic mixer. We have some different categories of mixer. For them, sometimes it can be improved to even let us say 0 dB. Noise figure, since conversion loss is 40 dB, noise figure is also 40 dB, and VSWR of the mixer is given as 2.6:1, and noise floor of the spectrum analyzer is minus 130 dBm. So, the spectrum analyzer can sense power till minus 130 dBm at rate of 60 gigahertz. Then what is the maximum and minimum power we can measure by using this system? The minimum power, it depends on SNR. Again we have to calculate SNR for the system, and since the device under test or antenna under test, it is connected to the subharmonic mixer. So, we can't change this one. So, only control we have on the transmitting antenna again, or maybe we can increase the transmit power. So, we will see then for different total antenna gain, what is the minimum power we can sense by using this spectrum analyzer for at different distances, and what limits the maximum power? Maximum power, it is limited by the non-linearity of the device. When we design any system, it can be microwave system or millimeter wave system, even a low frequency amplifier, we consider it as a linear device. So, that is why a low frequency amplifier sometimes we call small signal equivalent circuit or small signal amplifier. Now, if I increase the power, input power, in that case it can move to its non-linear region, and then we have to model it in different ways, and it will be associated with other high frequency components. So, maximum power would be then limited by the non-linearity of the devices are being used in the system. Here we are considering the minimum power to maximum power difference. So, it is calculated for this data set. So, dynamic range for this measurement setup, then it varies with antenna gain and distance because of the different SNR value. So, at 10 meter you see when the antenna gain is less than let us say 6 or 7 dBi, it can't sense anything, we do not have any dynamic range. So, to sense anything it starts from approximately 7 dBi, and now if I keep on increasing the antenna gain, so in that case this dynamic range will increase. So, maximum to minimum power, that can be the dynamic range, it is the difference between the maximum and minimum power that can be sensed by this system. Now, obviously, if we decrease the distance let us say to 0.5 meter, in that case we have some dynamic range even for 0 dBi gain, and if I increase the antenna gain, then dynamic range increases. So, when we are going for any measurement for any antenna or any other things, that time also we have to keep in mind what about the what is the SNR, and because the dynamic range it also depends on SNR of the receiver. So, here you see for non line of sight communication an extra 30 dB fade margin is suggested to compensate severe fading effects because of multipath, human shadowing, etc. For these plots we consider line of sight communication. Next, link budget. So, typically we are considering for indoor model. So, link budget it's basically signal power plan under the given condition. You do not have any control over noise figure and the noise contribution, then depending on the receiver to transmitter's maximum separation, what should be the minimum antenna gain value, what should be the minimum transmit power. So, all these are calculated using this link budget. So, the calculation let us say we are considering at 60 gigahertz, it starts with the path loss calculation. Now, for the first 1 meter we will consider the path loss, it is 20 log 10 4 pi f c by c. So, if I put f c equal to 60 gigahertz, it comes 68 dB. Average noise power per bit n, this is equal to minus 174 plus 10 log 10 of RB. So, this 174 how it comes, you see thermal noise at the input, it depends on the noise temperature T and the noise bandwidth B, KTB. Now, if we put the value of K and T and calculate thermal noise power per hertz, then you put K equal to Boltzmann constant, that is 1.381 into 10 to the power minus 23 watt per hertz per Kelvin, and if nothing is specified we will consider T equal to 290 Kelvin, it is called the room temperature. So, put the values here, then it would come 4.005 into 10 to the power minus 21 watt per hertz, and if I convert it to decibel scale dBm, minus 174 dBm per hertz. So, B bar we are calling normalized bandwidth of 1 hertz. Now, if we have a rate RB, then we need to add the contribution because of this bandwidth, and it is 10 log 10 of RB. RB is the GBP, this is the system payload bit rate. So, then average noise power per bit in dBm Pn, this is equal to n plus Rx, noise figure in reference to the antenna terminal. Tolerable path loss PL, the previous formula, in addition to that we are considering M shadowing, that shadowing effect. So, for human body it can be 15 to 20 dB. So, depending on scenario, we have to put a suitable value for M shadowing, and here S is the minimum signal to noise ratio or EB by small n naught for the additive white Gaussian noise channel, and IL, this is the implementation loss in dB, including filter dispersion, phase noise, if there is any frequency error. So, everything is taken into account in IL. Then we can calculate total loss from here. Then maximum operating range D, it can be given by 10 to the power PL divided by 10 into n, where n is the path loss exponent. So, for ideal case in free space n is equal to 2, but for indoor model n depends and it varies from room to room. We have to use some experimentally fit value for small n. Here are some examples suggested for IEEE 802.15.3c standard. For line of sight scenario, consider PL naught 68 dB, path loss exponent n equal to 2 and M shadowing just 1 dB. This is called shadowing link margin. But for non line of sight scenario, path loss at 1 meter, same value 68 dB, consider path loss exponent small n equal to 2.5 and shadowing link margin equal to 5 dB. So, these are some suggested value for this IEEE standard. Okay, so we will take a break, then we will calculate a link budget for a given system. Thank you.